Now what we want to do is the pooling layer. What pooling layer does, again let's go to this image. This is let's say this is our image, or this is our feature map. Let's say we extracted this from another image or feature map, and we created this feature map. And let's say as we move forward with our convolutional layers, it will create more and more feature maps. So let's say in one convolutional layer we have 120 kernels, and every all the 120 kernels will create 120 feature maps. So our input image for the next convolutional layer will have 120 channels, and if the size of the feature maps remains same, then there it will be CPU intensive. So what we will do, we will attach a pooling layer. It will have another kernel which will, let's say this is the kernel, and it doesn't has to have it's not a kernel, it's like a window, or it doesn't have any features on anything in it. It's just a shape. And what it will do, it will take the entire thing, whatever in there in that original image or feature. It will take that, it will calculate the max or average depending on the algorithm we choose. Let's say it's a max algorithm, so it will take the max of this entire thing, and it will give it will put it in the same corresponding location in the next output image. So same way it will move based on the strides that we set, and it will give the max or max of that next pixel. So that way we will, if it's a 4 by 4 pixel, then it will do it like this, it will do it like this. Let's say we set the stride as 2 pixel. So let's say if 2 pixel is this height, so it will move like this, it will move like this. So that way what will happen, the output image will be smaller, and it will look like a scaled down version of the input image. So that is what a pooling layer is. Using the pooling layer, we will have the full control of how much we are shrinking and what will be the next size of the image. So let's create a pooling layer. Okay, so before moving forward, I wanted to add another thing, which is we want this entire thing to be inside one TF scope, name scope, so that this entire process will show up under one block in our tensor board. So what we will do, just a simple step, which is with TF dot name scope. Let's name it conv as scope, and that's it. So whatever there inside, we will just put it inside the width command. Same goes for here. Initially we'll start with tf dot name scope, and we'll add pooling. I want the names to be capital here, and as scope, and that's it. So whatever we will do inside this name scope. Let's remove the pass. So we have the structure. Let's add the parameters. Same goes here. We need our input layer for the layer we want to attach. Now the parameters that we will need is the window size. The window size is called as k size, and we'll give it like now the window size can be 4-dimensional, which is height, width, batch, and channel. So it can shrink in batch dimension, it can also shrink in channel dimension, but we don't want any of those. We don't want it to shrink anything from the channel, we don't want to shrink anything from the batch. So we will keep one there, and we will keep we only want to shrink in the height and width dimension. So 1 2 2 1, and if we, as we are setting 2 and 2, so it will shrink 2 pixel to 1 single pixel, and from the height or width, and 2 pixel from the width or height in this width and height to 1. So it will be 4 cross 2 cross 2 pixel, means 4 pixel it will get from the height and width dimension, and it will calculate the max or average from that, and it will give the average or whatever we want to select to the feature next output on the corresponding pixel output pixel. So this is the case size, and same goes for the strides. Strides is also 1 comma 1 comma 1 comma 1, and we don't want to move 1 pixel at a time, we want to move 2 pixel, because our window size is 2 cross 2 in width and height dimension. So if it is 2 cross 2, the next step we want to take should not overlap what we already have. Let's say this is the position of the window now, and the next position should start from here like this. So it has to move 2 pixel because the window size is 2 pixel, so it will not overlap in between. So the strides will be same, and or we can also move it like 4, so then it will be 16 times smaller than the original one. 4 into 4 16, so then the entire output image will be 16 times smaller than the input image, but let's keep it in 2 cross 2. If we want more reduction, we will apply another pooling layer that will make it a 16 automatically. Padding equals same. So while moving the window, we will again face the same problem which we already faced in the convolution layer, that last edge problem, so which will reduce the dimension a little bit. So we want to avoid that, so we will make the padding same. So that's all the parameters that we need. Let's create the pooling layer. Return tf dot nn dot, let's use the max pool, and the value will be the input layer. The k size is the k size we have, strides is the strides, and padding is the padding, and another thing is the name. Name is, we want to put it as pooling layer, and that's it. We have our pooling layer. Now what we do, we have our convolution layer, which let's say we have an image and our convolution layer is on top of it, which is creating a feature maps, multiple feature maps on top of it, and there is another convolution layer which is calculating features of the features, the feature map, and this convolution layer, after this we have a pooling layer which is reducing the size of the feature maps, and at the end we want to, whatever the features that has been calculated, we want to classify what type of image that we have seen. So we want to classify that whatever there inside the image. So for that we need we need to apply the fully connected layer that we have already seen in our first or second tutorial. So to apply the convolution, to apply the fully connected layer, we need our input to be one single vector, but the output that we are getting from our pooling or the convolution layer is a two-dimensional, or you can say it's a three-dimensional if you include the channel and exclude the batch dimension. So it's a three-dimensional image. So we have to convert that three-dimensional into one single vector. So how we will do that? We will take each and every pixel for the entire image, including the channel. We'll put those pixels in a single vector, and we'll supply that to our neural network, which is the input of the fully connected layer. So for that we have to apply some computation which will do that operation. that will call the flatten layer. So it will take the 3D or 2D image, it will squash it to a single vector and it will supply it to the input of the fully connected layer. So for that we'll have this flatten layer, input, we need the input for this which we want to flatten, and that's it. We don't need anything else for this. Again, let's add the width, tf dot name scope, and let's name it flatten as scope. So we have our name scope. What we will do to squash the image, we need to know the output size of the vector. So to get the output size of the vector, it will be the output will be the same number of pixels that is available in our input image. So our input image has height, has width, has channel. So each dimension there is 1 pixel. So we have to calculate the total pixel. So that will be the height into width into the channel, whatever the length of the channel. So we can get that from the input shape and from the last 3 dimension size of the last 3 dimension from the input shape. We can multiply those 3 and we can get the output of the flattened layer. So the output, so new size will be equals input dot get shape dot as list, and let's put it as, instead of new size, first let's put it as an input size, and then we will use the new size equals input size minus 1 multiplied by, so it will get the last one, just copy it, paste it, multiply the paste it, and that's it. So it will be 3, it will be 2, so it will be the channel, height and width. These 3 we need for our flatten layer. So now to flat the layer we have to reshape it. So we'll return the reshaped one as tf dot reshape the input layer that we want to reshape, which is input layer, comma the shape that we want to supply. So the shape will be whatever the input image shape that we calculated plus the batch dimension. The batch dimension could be anything, that will depend on the input that we supply to the network. I mean, how many input that we supplied in bulk, so that will be the batch size. So batch size we cannot decide on the before running it. So to make the batch size dynamic, we will supply -1, and the next size will be the vector size, which is the input size of the network. So that will be new size, which is one single vector. So previously it was the batch dimension plus the height, width and channel. So now it is the batch dimension, which is indeterminate, and only the input size, one vector. So it is so we have reshaped it, and that's it for the flattened layer. Now let's attach the dense layer. Dense layer is the same thing that we have done in our previous tutorials. Dense layer is nothing but the fully connected layer, which is, let's call it DENSE, dense. Let's remove the pass, and to create the dense layer we need to create the weights. Weights equals TF. First we need to select the parameters, which is input layer, comma the number of output for this dense layer or this fully connected layer, which is output size, and let's add the summary variable here also, equals, and the output, let's put it default is 10 or 32, let's say. Tf dot variable, and let's initialize it with a random normal. Shape will be the input size. For that we have to calculate the input size. Input size equals input layer dot get shape dot as list, and we want to get the last one, which is the new shape that we created. We don't want the batch dimension, so -1 will give the last one. And to create the weight, we have to give the input first, then the output size. So we have the weight variable, let's name it dense weights, and we also have to create the biases. The spellings are good, or whatever the spellings are, what is the correct one, anyway, it doesn't matter as long as your code works. Tf dot random, and we want to give the bias as output size, and let's name it dense biases. Now to create the fully connected layer, we just have to matrix multiply this weight with the input layer. So to create that, let's directly return this tf dot matml input comma weights and plus biases. Okay, so if I recall, I forgot to do one thing, which is I forgot to attach the biases here. I created the biases in this place, but I forgot to add the biases in the conv layer. So this will complete the conv layer, and that's all. Okay, one more thing, that is, before returning, let's check the summary flag. If it is true, then tf dot summary dot histogram and weights dot name comma weights. So it will write this in our tensor board. So we have all our layers required to create an image classifier. So we have convolution layer, we have pooling layer, we have flatten layer, we have fully connected or dense layer. All we need is transfer functions, which are the activation functions. Let's add this. This is very simple. Let's add a width tf dot name scope activation as scope, and I want to I want to copy paste this here also and here also. It's because it will be same for everyone. Now what I will do, return tf dot nn dot what we need relu And what we need here as an input is the input layer. We'll supply this here also, and I want to give a name here, ReLU, so that inside the activation block we can see what is this activation layer is doing. Let's just copy it here and everywhere. This input layer also with the comma and the comma, and instead of ReLU it will be soft. So softmax. This will be sigmoid. Let's just change the name to softmax. And this one is sigmoid. So these are the activation function we will use to scale our output of our networks, for each and every layers. So that's it. We have created our network builder. In the next tutorial, we'll use this network builder to create our very own image classifier, and it will be very simple to create our image classifier using this network builder. It will be few lines of code, just stacking each and every layer one top of it, and we'll use a Kaggle dataset like cats versus dog to train our newly created network how to differentiate between cats and dogs. So see you guys in the next video.